not done the work and nobody asks about it, you don't want to spend time copying it down right now, because it usually, if I remember, and I did remember now, is videoed and you can check it later. Everyone is good with those? 7, 8, 9, 9. Yeah? Excellent. And there is, oh, B doesn't appear to have an answer. It appears to be this mess over here. So let's fix up 9B right now. It is 48, a to the negative 12, 6 to the negative 8. So it is 6 over a to the 8th. That 6 looks like a B. 6. Just let me double check that. Unless other people got that, then I can not waste my time double checking. Yeah? Okay. Good. Now we come to where it actually gets difficult. Yes? The answers are highlighted in yellow. All the rest of this is work that kids have asked me to do. There's that answer, and there is that answer. Now, I am 100% sure somebody is going to ask about one or two of these. Oh, there is that answer. Again, there's no point trying to write down all the work. And also, basically, if you can do one or two of these, they're all the same, aren't they? Right? Because you're using the same laws. So would anybody wish to ask about any one of these? And then I can go through it a little bit, and I can erase all this mess so it's tidy. Everyone is happy with 320p to the 6, q to the 3, negative 8m to the 6, and 675 x10, y14. Everyone's happy with the top three of their work. If they didn't do it, they are not trying to copy it down now, because you can see how much work it is. You might write down the answers and then go back to it later and see if you could get to those answers. That would be perfectly acceptable. Yeah? Okay. And then these bottom three are a little bit snakier. There they are, and I am willing to go over any one you wish to see, of course. Everyone is happy? Nino?
D. I don't know.
12, or which D? 12D? Yep, okay. So let's have a look at that one. Let's erase it all up. Okay. So when you're doing these, you got to remember, you have to apply all the laws, yes? So some of you will want to multiply right here first. But you don't multiply first, because I also said you have to remember all your previous math. And the first thing you're supposed to do when you are faced with multiple operations is anything with an exponent, yes? This exponent is going to affect, I'm going to use yellow to color code, that yellow exponent affects this entire yellow base. So I cannot multiply this 5 here until I deal with that yellow exponent, yes? Now, since that yellow exponent is affecting the whole base, it's going to hit the 2, the x, and the y. A big mistake that students make when they are doing complex exponent questions like this is you try to hold the knowledge in your head. You have some sort of weird allergy to writing down work. I know this because every time I give questions to kids, the first question out of your mouth is, do I have to show work? The answer in math class has always been what? Yes, and yet every year kids ask, every time. So you're not touching the first one yet, so you rewrite it. And now we're going to deal with the yellow one. And I'm going to keep it highlighted so you can work with it. 2 cubed is 8. X cubed is x cubed. Y squared cubed is y to the 6th. Yes? And then we have, now you will notice down here, I have a blue exponent and a blue base. So I must deal with that exponent as well. That will be the blue section. 10 squared is 100. X cubed squared is x to the 6th. Y to the 8th squared is y to the 16th. Now, if I made just that yellow part a single question by itself, everybody should have been able to get to here, yes? And if I made just that blue section a single question by itself, like I did earlier on this worksheet, no problem, yes? All right, now, I have numbers here that I will circle in red that are not exponents, are they? They all work together. What is negative 5 times 8?
Negative 40.
Negative 40 over 100. Those are my numbers. They aren't affected by exponent laws, except here. And now we can deal with the exponents. And I will keep them green. X's will be green. On the top, how many x's do I have?
7.
7, because that is exponent law 1, yes? There are 7 of them. The y's will be, what color haven't I used? Pink. How many y's are there?
11.
Y to the 11th. On the bottom, x's are green. There's only one of them. X to the 6th. There's only one y. Y to the 16th. Now, yes, Paige. Negative 5 times 8 is negative 40. Because this is multiply right here when there's no sign, right? Now, all we do is simplify. Negative 40 over 10 is what? Negative 4. Negative 40 over 100 is negative 4 over 10, which is? 4/10. Yes, but we don't use decimals in the 10th grade. We keep it as fractions. So 4/10 is what fraction?
That's a fraction.
Hmm?
4/10 a fraction?
Yes, it is, but we simplify in math class.
2/5.
Thank you. Negative 2/5. 7 x's up top, 6 x's on the bottom. What do I get to do with 6 of these x's? I get to cancel. Now, if you memorize the law, 7 minus 6 is 1. 1 is positive, so it can stay up here. I, of course, do not recommend memorizing the law. I recommend understanding what is actually happening. And there are 7 x's up there, x, 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 6 x's down there, x, 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 x. These 6 disappear, and 6 of them disappear, leaving you with 1 x. Now here, you're going to subtract. 11 minus 16 is negative 5. But then, where do I put the negative 5? Because you're only memorizing laws. There's 11 up here, but there's 16 down here. So these will all disappear. How many of that 16 will disappear? 11 of them, leaving you with how many? 5. And since it's a positive 5, we would leave it as positive 5. Even though it's in the denominator. Okay? Once again, I stress, every teacher teaches you guys the exponent laws. And you all, exponent laws, must know them. Take an extra second to learn what they actually mean. Because then, exponents really aren't that difficult, are they? You got the same thing on the top, same thing on the bottom. You get to cancel them. Right? Okay. Any of the others here? We're good? All right, now listen, this is kind of weird here. I explained to you that the exponent laws were really important, yes? But for the most part, we don't do a lot of math like this. For the most part, for you people, the exponent laws become a tool that you need to solve other problems, okay? The exponents won't be very large. Usually. And it's almost always multiply and divide. We don't have a lot of this move here in reality. Okay? So we've done now 35, and there's like 20 on here. We've done 660 about, plus all the practice work we did. Are we comfortable? Because I don't want to belabor the point. As you can see, we've got 8 more units to get through. And we will be practicing exponents as we go. Are we all cool? Okay, you will notice if you look at my list over here, you will see a quiz down here. We have just finished 112. So if you look on your outline, we did basic rules. We've now done complex rules. That was February 5th. And here we are at February 6th. Today, the real number system, which for you people will begin on page 19. Now, that is this is another one of those things that seems fairly unimportant, except all these words and names are things that will become more important as we go further. And I, of course, do not tell little stories and call things princesses that are breaking out of castles and things like that. I teach math, and I will be using these real mathy words. So you need to know what they mean, okay? Because if you do plan to go any further in math studies, your university professors are not going to tell you a story. They are going to do math, okay? All right. Even if you don't go to university, you go to do something else, almost everything has a math component. And the teachers don't tell stories. They talk about what is actually happening. So you actually need to know the real words. So let's go on, shall we? Please notice the real number system. That is an important word there. Real means real. These are the numbers that we use every day. And you think it's simple, but of course it isn't. If I were to ask you to all, like in grade 3, start counting with me, and I would clap my hands, and as soon as I clap my hands, we start, what is the first number you would say? 1. All of you would say 1, right? Because that's the first number. None of you, well, 1 or 2 of you would go, just to be wise asses, 0, 1, 2, 3. But 29 of you would say 1, right? Okay. That is naturally what we would say. So that is what the math world has decided are natural numbers. They are the numbers that start at 1. What is the next number? 2. What is the next number after that if we count? 3. When could we stop this list?
Whenever we want.
Huh?
Whenever we want.
Yeah. So when would we stop it?
Well, I vote now.
You can't stop it, can you? Because where will this list end? Never. You'll get to infinity. Does infinity actually exist? No, because you'll never get there. Everybody understand? So these numbers, 1, 2, 3, and so on, up to infinity. So how many natural numbers are there? There is an infinite amount of natural numbers. Is everybody cool? Right? So if we were to draw a representation of that, we would have to draw like a really big box. Everybody agree? Everybody understand? Okay, now here's what's weird. Even though there is an infinite number of natural numbers, there is the fewest natural numbers, even though it's infinite. Does everybody understand? It's a little mind-blowing. How can something be infinite yet also be the smallest? But it is. Everybody cool? So what I like to do over here is I like to draw myself a little box with an N in it to stand for natural numbers. And that covers all the natural numbers in our universe. 1 up to gazillion, billion, quadrillion, manillions, whatever. Everybody cool? Now, if that's the smallest, we're going to go to the next biggest. The whole numbers. The whole numbers are the natural numbers plus one more number. What number? 0. 0 plus the naturals. Up to what? Infinity. So aren't there also an infinite number of whole numbers? Yes, there is. But it's, for lack of a better word, technically just ever so slightly bigger, right? Because it gets the 0. Everybody understand? Okay. Next level, integers. Now you're smart people. Natural, then the whole numbers are the naturals plus something else. So what are the integers?
Natural plus negative.
Close. Page. All the negatives and the wholes and the naturals. So what you said was so close, but you forgot 0. 0 gets to be an integer. So integers are the wholes plus the naturals plus the negatives. Now what's the smallest number we can get to? Negative infinity. So it's going to be negative, my pen's not working, there we go, negative infinity all the way up to positive infinity. How many numbers are in that? Guess what? It's still infinity, but it's still more infinity than the other two. Everybody understand? That's why math theory is actually kind of neat. So here I'd have the integers, and you will see that the naturals fit in the wholes, which fit in the integers. Everybody understand? It's kind of like those little Russian dolls. Now, I'm not being culturally insensitive. I know other cultures have those little dolls, but I don't know what they are called anywhere else. I know Ukrainians have that, lots of Slavic countries have it. But I'm just saying Russian because, it's not cultural insensitivity. It's a lack of knowledge. Everybody understand? Nobody is offended. Nobody is Slavic and is bothered by the fact that I didn't mention their particular nesting dolls. Good. They have a name. I just can't remember that either because it's a Russian word and I can't remember it. I used to know it, but I don't now. Now, up to there, everyone should be cool, right? Those are the numbers you've worked with forever. Now, what do you notice I have not mentioned in the natural numbers?
Fractions.
I have not mentioned a fraction, have I? And I have not mentioned fractions' ugly cousin decimals. I hate decimals. They are weak-minded. I don't want you using them if you can avoid them. Does everybody understand? Stop using decimals. I will tell you when it is okay to use decimals. Otherwise, we use what? Fractions. Because fractions are better. But I have to acknowledge the fact that decimals exist. Now, the reason can pinpoint for you the exact point in your mathematical journey where math became difficult. And it was the point where your teacher, up until then, you had only been dealing with natural numbers, yes? 1, 2, 3, 4, 5, 6, 7. What's 7 minus 3, little, choose a name. Little, Jimmy? Have you ever actually met a kid named Jimmy? Really? You know a kid your age named James that goes by Jimmy. The kid's name is Jimmy. It's not James. Is the kid from another country and that's the name that kid has chosen?
No.
The kid's name is Jimmy. Like on his birth certificate, it says Jimmy.
I think it's Jay. I'm pretty sure his real name's Jay.
Pretty sure his real name's
It's Jay.
Jay. So he's gone from Jay, which is one syllable, to Jimmy, which is longer. Nicknames are not, whatever, I'm not going to argue. Anyway, fine. Ezra says we're going with little Jimmy. Little Jimmy, what is 7 take away 3? And you, as little Jimmy, went like this. 7, 1, 2, 3. 1, 2, 3, 4. Now, when I was taught math in 1981, when I entered I'm the worst kind of liar. In 1979, 1980. In 1980, when I entered kindergarten, that is how I did math, right? That's how we all did math. The difference between you people and me is I didn't have jump math. I actually learned math. You guys are still counting on your fingers. That's okay. There's nothing wrong with that. It's fine. We learned the math, so we stopped counting on our fingers. When math went crazy for you is the day that you walked in there ready to kick ass. 7 minus 3, I got it, Mrs. Bad Crumble. It's 4. And she was like, good job, young person. I'm very proud of you. Except now they say, good job, young human. That's the new phrase for it. I can't stand that phrase because there's no one else on the planet other than humans. So why would I call you all humans? It's not like the aliens have arrived yet because, of course, when they arrive, we will be either exterminated or enslaved. So it won't matter. Back to where I was. Mrs. Bad Crumble, 4! And good job, little Jimmy. Now, sit down and get prepared for today's math lesson. You were like, yeah, bring it. 8 minus 5, no problem. 13 minus 7, I got this. I'm all up in this. And then your teacher drew the number line, and they put a 1, and they put a 2. And you're like, yeah, 1 and 2. And then they did this. And you went, what the hell? There's nothing between 1 and 2. 1, 2. The only reason you understood that is because you all grew up with parents who didn't belt you. Your parents said, go clean your room. And you said, no. And they said, go clean your room. And you said, no. And then they went 1. And you were like, what? And then you went and cleaned your room. And then you didn't go clean your room the next day. And they went 1, 2. And then you went and cleaned your room. And then, now your parents, here's a little hint. Your parents never wanted to get to 3. Because they didn't know what they were allowed to do when they got to 3. So what did they start doing when you hit 2 and you said, no, I'm not cleaning my room? They went 2.5 and you went, what the hell is that? And then Mrs. Bad Crumble cut that in half. And then she 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 cut that in half. And then, without actually telling you, what she really did was explain that between 1 and 2, there's a whole nother infinity. And you guys went and dropped your pencil. 90% of you. Because right there you decided math was not for you. How close am I to most of your experiences? A little close? Spot on? Yeah. Don't be that way. You needn't fear it. So, the rational numbers. In that word rational, you see the word ratio. Ratio is just a fraction, yeah? That's all rational numbers are. They are fractions. They are any number that you can draw this way. X over Y, some number over another number, as long as 2 rules are met. X and Y are integers, which we already know what they are. And Y doesn't equal 0. Because, of course, we know you cannot divide by 0. All right? And that's it. That's what makes a rational number. So, is 7 a rational number? Yes, of course, because 7 really should be 7 over 1, yes? Everybody cool? Is 2.3 over 4.7 a rational number? But I said X and Y have to be integers. Are those integers? Or are they integers?
I don't know, dude.
Of course they're integers. Why? What if I multiplied this by 10? What would I have?
4 numbers.
I'd have 23 over 47. Isn't that a rational number? So is that a rational number? Yeah. Let me ask you this one. What is 1/2 over 1/8? Is that a rational number?
Yeah.
Of course it is, because that is 1/2 times 8 over 1, which would get me 8 over 2, which would get me 4, which is a rational number. Is everybody cool? If it's a fraction, it's a rational number. End of discussion. Doesn't matter what's in the fraction, it's a rational number. Everybody good? Now let's talk about his ugly cousin, the decimal. A decimal rational number does two things. One, it ends. What do you mean by it ends, Mr. Myers? It ends. 1.5. The decimals end. It's rational. Because, of course, you know that's 3 halves, right? 3 over 2. 27.3247. Does that end? Yeah, it stopped at the 7, right? Because that is 3,247 over 10,000, which is a fraction, right? Everybody cool? That's the easy one. The other one, and this is the one that causes problems, it repeats. For example, 0.33333 forever. It doesn't end, does it? But it's still rational because that's 1/3. Everybody cool? 1 over 3, they're both integers, so it has to be rational, so its decimal is rational. Now, where mistakes happen for you young folk are things like this. 0.4782 and just a line over the 2. Is that rational? Yeah, because the 2 is repeating. Okay? What about this one? 4782, and then I just put 3 dots.
It keeps going.
It means it keeps going, but I'm not writing any more numbers. So is that rational?
Yeah.
Does that repeat? 4782. All these dots mean is that it keeps going. So does it show a pattern?
No.
No. What if I did 478, 478, and then put the dots? What would you say that is? You would say that is rational because it looks like it's going to repeat. Do we know with either one of these? We do not know. We can only guess. Everybody cool? All right. So that's the rational numbers. Now, the rational numbers fill up all of these. And now, of course, logically, if we have rational numbers, we must have irrational numbers. They're the crazy numbers. You don't know what they're going to do because they're irrational. Get it? I hate first block. Not you people, just first block, because you're bad with the jokes. By last block, you're all like this from school. And I could sit up here and make fart noises and you would all laugh. I love last block because the audience is easy. First block, it's too hard. Irrational numbers are every other number. Mr. Myers, what more numbers could there be? For our purposes, irrational numbers, except for pi, because we all know pi, except for pi, the irrational numbers for us is anything with that root symbol that doesn't work. Here is what I mean. Huh?
Negative numbers.
Well, no, we'll talk about that in a second. Irrational numbers. If this doesn't work, it's not rational. So, is there a square root of 4?
Yes.
What is it?
2.
And 2 is rational, so that's okay. This is a rational number. Rational. Everybody cool? Okay, what about this one? Square root of 1.44. Do you think that is rational or irrational? Do it with your calculator. Do the square root of 1.44. What do you get?
59.
Pardon me? You get a fraction, don't you? 6/5. right? So that is rational. What about the square root of 3? What shows up on your calculator? The whole screen fills up with decimals, yeah? Do they repeat? It's like 1.73284, blah, 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 yes? This is irrational. There are infinite irrational numbers as well. The square root of 2, the square root of 3, the square root of 5, the square root of 7, the square root of 8. All irrational. Everybody cool? And of course, pi. There's another very famous one that we use in finance. It is a little e with an x up here. That's approximately 2.78. Pi is approximately 3.14. But they are only approximations. These decimals go on forever. Pi is at like 3 trillion decimal places or something and hasn't repeated. It's not going to. Now, I know that that's dangerous to say it's never going to, because maybe at the 18 quadrillionth decimal place, the pattern will start again. I don't know. Nobody does. But there's a computer at MIT or something that they started doing pi like 40 years ago, and it's still doing it. All it does is sit there and do pi. What? Pi is the answer you get when you take the circumference of a circle and divide it by its diameter. Now, all of you will say, but that's a rational number. It's a fraction, right? But it's not. Because the circumference and the diameter never make integers. If the circumference is perfect, the diameter is going to be a little bit off. Pi is that value. And strangely enough, many mathematical cultures used pi without knowing it was pi. Are we all cool? We can use the words. If I talk about these things, everyone's cool. The reason we use them and we make the distinctions is mostly for statistics, right? For example, if I'm doing a graph of people, could I use integers for the graph?
Yes. No.
Why not?
Because there's no negative people.
There's no negative people, right? Could I use fractions for the graph?
No.
No, because there's no half people. People say they have a half brother, but that doesn't mean an arm and a leg comes walking through the room, right? If you lose your arm in a combine accident in a farm, you're not 3/4 of a person. You're still a person.
Just some more rational numbers or negative numbers? Some more rational numbers or negative numbers?
Is there more? Are you asking me, is there more rational numbers than negative numbers?
I think some are rational numbers, all the negative numbers.
Oh, can there be negative irrational numbers? We'll get to I said we were going to get to that right now, yes. Can you have a negative irrational number? Well, you can kind of, because, for example, negative root 3 would be irrational, because that would be negative 1.73 blah. But you cannot have that. That doesn't exist because there is no, that symbol means we need two of the same factors, yes, which is what we're doing on the 1.5. We're going to get into this more specifically. You can't have a square root that's a negative, because you can't have the same thing, because if you have the same thing, two negatives will give a positive, not a negative. This, though, ladies and gentlemen, even though it's impossible, is needed to do some math very high up. And this is an example of a fifth set of numbers. Are you ready for their name? These are the imaginary numbers instead of the real numbers. Now, I am your new Mrs. Bad Crumble, because Mrs. Bad Crumble did 1 and 2, and then it said there's infinity in between 1 and 2. Well, I'm now the one telling you that just when you start to get comfortable with all the real numbers, someone's going to introduce imaginary numbers. And then you got to learn all the math that goes with them. But don't worry. That's not going to apply to any of you. Well, I shouldn't say that. It's very unlikely. Do any of you plan to be theoretical physicists? No? Do any of you plan to be mechanical engineers? Rockets into space type of thing? No? Do any of you plan to be electrical engineers? Not electricians, electrical engineers. No? All right, so you don't have to worry about imaginary numbers. Okay? Now, if sometime between now and then you decide maybe I do want to send a rocket to Pluto, then you're going to have to learn about imaginary numbers. All right? All right. Turn the page over. You should all be able to do 1A by yourself in about 5 seconds. This is where I check if you actually paid attention to Mrs. Bag Crumble's lessons on place value. 1A, that's all I'm going for. You shouldn't need a calculator to do it. Would anybody like to volunteer their answer? 3 over 25. That is absolutely correct. I assume that it was gotten by going 12 over 100, because that is 12 hundredths, and then dividing by 4 to simplify to 3 over 25. We can all do that, yes? Even if you forgot when I said do this in 5 seconds, you now are like, oh, of course, tenths, hundredths, thousandths, right? No problem. Easy peasy lemon squeezy, right? So if I gave you 0.257, what's that as a fraction?
0.257.
No, that's a decimal. What is it as a fraction?
0.257 over 1,000.
Not 0.257 over 1,000.
257
257 thousandths. Right? We can all do this. We all remember grade 6, yeah? Okay. Now, some of you have been taught the trick to do this. What does this little line mean? That 1 will go on. For how long?
Okay.
Ever. Now, since it repeats, it must be a rational number, yes? Which means we must be able to write it as a fraction, yes? What is that fraction?
1 over 9.
It is 1/9. Now, why?
Explain it. If you keep times it by 9, it'll be 9 9 and 9 repeating.
If you times what by 9?
This number.
This number, if you multiply by 9?
Yeah, it'll just keep repeating 9 and 9 and 9.
Okay, so if I multiply this by 9, it would cancel. Okay, that's one good definition of it. Right. Anybody got another one? How many people knew that it was 1/9, by the way? And why did you know it was 1/9? Because my teacher told me that if it repeats, it's over 9. Is that why? I'm not putting you down. I'm just wondering, is that why? A lot of kids have heard that. If it repeats, it's over 9. Of course, you should know the reason why, right? If that wasn't there, then that would be 1/10, yes? Everyone agrees, right? But it is there. So it's actually slightly bigger than 1/10, yes? Right? Slightly bigger. So it's still 1, but this, according to our rules of rational numbers, this denominator has to be an integer, yes? Well, what's the next integer around 10? 9 and 11, yes? But 1/11th is smaller than 1/10, yes? Whereas 1/9 is bigger. And since this is slightly bigger, it has to be 1/9. Everybody cool? Little bit of number theory there. What do you know about letter C? Page. You know that the first 4 digits repeat, right? Because it shows that. You also know what else? Does it end right there? No, you know it's going to carry on, right? What is the assumption now that we have to make?
There's no repeating sign on top of the 2, so it might change.
It might change. But according to the evidence we have, it's going to be 2 repeating, right? which would make it what? 2 over 9, just like we had up here. But that technically is an assumption, yes? Is it an assumption supported by the evidence we have? Yes. So are we okay with it? Sure we are. Now look at D. What's weird? Page? Just the 4 repeats. So it's 5, 4, 4, 4, 4, 4, 4, 4. So is it 54 over 99? It is not. Why? Because that's the guess every kid gives. It's 54 over 99. It has to be. But if you do that with your calculator, what do you get? 54 divided by 99. 0.545454, right? They both repeat. What's the only thing that repeated here? Did the 5 ever repeat again? Really?
Oh, the calculator one.
On the calculator one it did, because that was 54 over 99, right? So in this one, there's one thing we have to do, and it is a bit of a trick. It's going to be over 99, because I got 2 decimals here, right? That's 54 over 100, right? So I got to have my 99 there. But here's where it gets weird. The numerator is 54, but you take away the 5, because the 5 doesn't repeat. So it's 49 over 99. I just put that in there. It's not important. I just like to talk about numbers sometimes because I'm a math nerd. Yo. 54 was what we started with, but we take out the 5 that doesn't repeat. So if it was 0.67 repeating, it would be 67, but I'd take out the 6 because the 6 doesn't repeat. So 61 would be my numerator.
Oh, not just actually taking out the 6. You're actually
Subtracting it, yeah. Was that a hand up, Ryan, or a stretch? Cool in the gang. Are we all good? All right, now listen, please. On this page, there are 7 questions. All I want you to do is give me the right category. What are the categories? Natural, whole, integer, rational, irrational. You got 1 in 5 shot. Go. Then we're going to talk about the right answers. Then I'm going to give you your work for the day. If you don't know, go. If you don't know what a symbol means, what should you do? Ask or leave it blank, right? Because there's more stuff going on here than just the categories of numbers. And as always, everything will be explained. All righty. Excuse me, I have to set a timer. Okay. This first one. What is it?
Irrational.
It is irrational. If you don't know why, it's no big deal. You're going to know in 2 lessons. What about this guy?
Natural.
Natural. Because it's all of the rest, isn't it? Because the square root of 25 is 5, yes? So that makes it rational. But it's also an integer. It's also a whole. It's also a natural. So if it's natural, does it automatically fit into everything else? Except irrational. This one, what's that?
Rational.
Rational. Why?
Because the decimal ends.
Because it ends. What is that as a fraction? What would it be over?
5 and 319,754 over a million.
Right, it would be over 1,000,000. What about D? We just did exponents. What's that?
Natural.
Ooh, intrigue. Is it an integer or is it natural? If it's natural, is it automatically an integer? If it's only an integer, is it automatically natural?
No.
No. So what is it? What does that equal, Nino?
-8.
-8?
Positive 16.
2 times 4. There's the kid that would do it. I told you somebody would do it. It's 2 times 2 times 2 times 2, isn't it?
Positive 16.
Which is
Positive 16.
positive 16, which makes it natural. What about 9?
Natural.
Natural. What about that?
Irrational.
No. Imaginary. It's the exact example I used. And lastly,
Rational.
do we know? No. So what is our assumption?
That repeats.
We assume that it continues to repeat, so we say it appears rational. Everybody good? All right. Now I've got very little work for you to do. 1 page, page 21. You will notice that over here I have the answers. That's for you. All right? That's your homework. Do that page.
So it should be rational. Or it should be natural.
Look at that, man. Give you guys... Yo! Yeah.
How is the first one irrational?
How is the first one? Irrational?
Yeah, isn't it just 3?
Square root of 12?
Or 6. Well, when I put in my calculator, it gets 3.46.
Not exactly.
Exactly.
It fills up the whole screen
Oh.
without repeating.
Okay, no, that makes sense.
So what is it?
So rational numbers are when they repeat, so you know that it's the same. And irrational numbers are when you just don't know what's.
Yep. Basically, Paige, if your calculator screen, if you're going to be using a calculator, and it fills up, it's an irrational number. Yeah. If it fills up with numbers that aren't repeating, exactly.
But if it's like 4.3,
that's rational.